All right, my name is Erica Nesvold. I'm from Team New Approaches. Here are my team members. They're also sitting down front here. This is Elmarie. Raise your hand, Elmarie. Adam and Nick. They'll be talking later. We are 3 planetary scientists and 1 poor machine learning scientist working together. So let's start off by talking about the Asteroid Grand Challenge, which was just nicely introduced for us. The other 2 FDL teams that you'll hear from today are both working on the first half of this challenge, finding and characterizing the asteroid threats to human populations. But our team was interested in the second half of this challenge, know what to do about them. What do we do once we've discovered that a hazardous object is on an impact course with the Earth? Well, a lot of people have thought about this question, and in the next few slides, I'll show you a cartoon picture of what they've come up with. So if you know that an object is on an intercept course with the Earth, then what you want to do to avoid this is apply a delta V, a change in the velocity of the object, either along its orbit or against its orbit. And if you apply that delta V with enough lead time, so if you have enough time between applying the delta V and the time that you're expecting to hit the Earth, then it'll alter the orbit of the object slightly, and it'll also change the time at which the object hits that intersection point, which means you're going to avoid that collision. So it's that simple from a very basic physics point of view. A lot of different technologies have been proposed for how to apply this delta V to an object. The one that most people think of course, is a nuclear explosion. You can also perform a similar instantaneous change of velocity with a kinetic impactor. And so this is just where you allow your spacecraft to crash directly into the object and change its velocity using just conservation of momentum. Another popular technology that's been proposed is the gravity tractor. So this is where you fly your spacecraft near the object without colliding with it, and you use the spacecraft's own mass to apply a gravitational pull on the object and change its velocity more slowly over a period of time rather than instantaneously like the other 2. So these are just a few of the deflection technologies that have been proposed over the years. So our work here is done, right? We just played on Facebook for the rest of the 6 weeks. No, we don't, although we know in theory what to do about hazardous asteroids, the problem is that while many of these technologies have been proposed, none has been fully built and tested in space to change the delta V of an object in space. And the other problem is that all of these technologies will take a lot of time to build and test, and that's time we won't necessarily have in between the time we detect an object on a collision course and the time it actually collides with us. They'll also all be pretty expensive to build and test, as are most space missions. And this means that we can't just develop them all today because, unfortunately, there's not infinite funding for NASA and for all of these programs. And so the question we need to ask ourselves is there any way to know which technology we're most likely to need? Then we could put all of our research effort and funding towards that object. So this is the question that our group is asking, is there any way we can figure out to prioritize which technologies we need to focus on? The challenge in answering this question is that different technologies might be more effective for different types of hazardous objects. So based on the object's characteristics, like its orbit, its size, and other characteristics, a technology that works for one object won't necessarily be effective in deflecting a different object. And so how do we go from the object parameters to the technologies that we'll need? If we can do that, then we can figure out, based on all the possible impactors, which technologies will we need. Well, to answer this question, we developed a model. And this model is called, this model can take in object parameters, like the orbit and the mass and other parameters, and predict which technologies will be most effective. And it can do that for any single object, which means that now that we've developed the model, we can input the distribution of parameters of all likely impactors, comets and asteroids, and the model will tell us which technologies will be able to deflect those objects. And so then that tells us which technology is most likely to be effective, and that's where we should focus our efforts. So this is the main goal that we had over the past 6 weeks, is to come up with this chart, basically, or at least a way to find that chart. But the nice thing about this model is that it lets us answer some other interesting questions too. For example, the model can tell us if this decision about which technology to use is particularly dependent on any of these object characteristics. So for example, maybe it turns out that the decision of which technology to pick is really dependent on the internal structure of the asteroid or comet. And then that would tell us that we really need models and observations to better understand the internal structure of these objects. The model can also tell us if there's any regions of the parameter space, so any types of these objects that aren't covered by any of the proposed technologies. And these would be the objects that we really need to worry about the most. So here's the basic framework for the model. This is also the outline for the rest of our talk. Our model is based on a machine learning algorithm. And this algorithm, we wanted it to be able to take in on objects' parameters and output which deflection technologies are most likely to be successful. But as you'll hear about today, if you understand machine learning very well already, then you need a training set in order to train your machine learning algorithm. You need to have a few examples of objects, in our case, that we know the answer to. We know which technologies will work for those objects. Then we train the algorithm on that training set, and then any future object that we ask it, it can tell us which technology we should pick. So in order to make that training set, we built a larger model around it. The first step in the first component of this model are orbital simulations. And these orbital simulations let us ask, for a given object's orbit, if we apply a random delta V at a random lead time, will we be successful? Will we hit the Earth or will we miss the Earth? And then the second component of this pipeline is a study that we did of the technologies that have been described in the literature. And this component lets us ask, for a given deflection technology and a given sized object, what delta V can we apply to that? So then when we put these two components together, that produces a huge training data set that we then used to train the algorithm. Adam's going to start us off by talking about the first component, the orbital simulations.
Thanks, Erica. Okay, as Erica already mentioned, the first step in this process is data. We need data. And in an ideal world, we would have lots of examples of humanity venturing out to hazardous objects and deflecting them and taking data, and we could run our machine learning algorithm on that data. But unfortunately, as Erica already mentioned, no such missions have ever actually happened. So as a result, we had to resort to creating our own data using orbital simulations and an n-body integrator. The first step in this simulation process is to create a population of impactors. Now, the population of impactors on the Earth is not particularly well known because the rate at which large objects impact the Earth is thankfully very small. So as a result, we took the well-known population of Aten and Apollo objects and slightly modified their orbits so that they would impact the Earth. Just as a reminder, Atens and Apollos are objects whose orbits cross that of the Earth when projected onto the Earth's orbital plane. But that doesn't mean that they impact the Earth or even necessarily come anywhere close to the Earth. So we took these orbits and we slightly modified them so that they would actually impact the Earth. And we found that we were able to do that in all cases in such a way that the inclination and the shape of the orbit was unchanged. Here's an example, or here's a plot of the objects that we used for these simulations. These are the Atens and Apollos. The x-axis is the semi-major axis of their orbits, which is the mean distance that the object reaches from the sun. And the y-axis is the eccentricity, which is a measure of the elongation of the orbit. And then color is just number of orbits that fell into that bin. Notice that as the semi-major axis increases, the lower limit on the eccentricity increases as well. This is because as an object's mean distance from the sun increases, its orbit needs to become more elongated so that it can get close enough to the sun so that it can hit the Earth. Okay, so now we have a population of impactors. The next step is to go back in time in the orbit of these objects and apply a delta V along their orbit in order to perturb the orbit. At this point, I need to introduce two small assumptions that we made. The first is that any point in an impactor orbit can be reached at any time. And this is not, in the general case, true. Certain orbits are energetically much more difficult to reach than other orbits. For example, a highly inclined orbit is very difficult to get to because your initial velocity vector that's contributed by the motion of the Earth lies within the plane of the Earth's orbit. The second assumption that we made is that objects cannot be broken up. And again, in the general case, this isn't true. You would normally have to worry about if you hit an object too hard to try and deflect it, you might waste some of your energy breaking it up into lots of little pieces, which are still all on an intercept course for the Earth. At the end of this talk, Erica is going to come back up and discuss some of our future plans for this project and how we plan on addressing these assumptions. Okay, so here's an example. This is a view of the solar system. The white ellipse is the orbit of an impactor, and if nothing were done about it, then it would impact the Earth at this point in a few months. So what our simulation does is it applies a delta V to the orbit of this object, which perturbs the orbit and makes it so that it will miss its rendezvous point with the Earth. And if this were actually included in our simulation, then this would be recorded as a successful deflection of this object. I should note that none of our deflections that actually occurred in our simulations were this big. The deflections were many orders of magnitude smaller than this, but you wouldn't actually be able to see the effect, so it's magnified for illustrative purposes here. Okay, so we do this for every orbit, and then for each of these orbits, we track the orbit forward in time, either until it hits the Earth or until 15 years have passed since the original unperturbed orbit would have impacted the Earth. And then at the end, we record various statistics on these objects, including their time of closest approach, the minimum distance to the Earth, and whether or not they hit the Earth. In the end, we ran over 3 million orbital simulations, and we used a variety of orbital parameters, delta Vs, and lead times. Over the course of this talk, we're going to be showing you a variety of 3D plots like this one, which will illustrate relationships between some of the input and the output parameters. But as Elmarie will be discussing in a few minutes, our end goal is to have a machine learning algorithm that can automatically detect the relationships between these objects without us having to ask it what the relationships are. So here's an example of one of these plots. On the x-axis, I'm showing the lead time, which, as a reminder, is how much time before the object would impact the Earth at which the delta V was applied. There's the delta V on the y-axis, which is how hard you hit it. And then the color bar is an indication of the success rate, which is what fraction of the orbits in that particular bin were successfully deflected from hitting the Earth. And here, blue is good. It means we successfully deflected it, and red is bad. So for example, on how to interpret this, if you have a lead time of 10 years, you would have to deflect an object with a few millimeters per second of delta V in order to achieve about a 50% chance of success. And in general, the behavior of this plot is as you might expect. If you apply the delta V further back in time, then you have a higher chance of success. And if you really want to have a high chance of success, then you hit the object harder. Okay, so now that we have these data, the question becomes, what are the deflection technologies that we can use that can apply these ranges of delta Vs in order to achieve these high levels of success? And in order to help answer that question, Nick is now going to talk about how we mapped from the space of object parameters and delta Vs to the technologies that are capable of achieving those effects.
Thanks, Adam. Okay, so several technologies have been proposed in the past few years, but because of the time constraint, our group decided to focus on the three main promising technologies, namely the kinetic impactor, the nuclear impactor, and also the more slow-acting technology known as the gravity tractor. And in order to get the delta V that each technology can supply us with, we did an extensive literature review. And all the calculations I'll show in the next few slides are based on equations that we found in this body of published work. Okay, so our first technology, the nuclear explosion. This technique relies on the vast amount of high-energy particles released during a nuclear detonation to impart a delta V on our asteroid. And those delta Vs are shown in this figure over here, with the asteroid size on the x-axis and the potential nuclear energy on the y-axis. And you might ask, why did we choose this range of asteroid sizes? The reason for that is because these are the asteroids that are large enough that they can cause extensive damage if there's an impact with Earth, but they are small enough that it can be difficult to detect these objects. In fact, it's predicted that for objects, say, less than 600 meters in diameter, we only know about 50% of the ones that we predict that the total number that are out there. So this is sort of a blind spot area, an important range of asteroids we have to consider. So from this graph, you can already see that the delta V's that you can expect from a nuclear impact are on the order of a meter or to high centimeters per second. And to give everyone a feel of what you would physically require to get these delta V's, I showed these three bars, each corresponding to a different launch vehicle. And their position on this graph is basically determined by the maximum payload that they can carry, or put another way, the maximum amount of warheads you can fit on one of these launch vehicles. The top two are indicated with question marks because they technically don't exist yet. The SpaceX launch vehicle is still under testing phase, and the NASA SLS is still under the development phase. So from now on, all the delta V's that we'll be considering are delta V's that are either on this bar or below that, because this is existing technology. Okay, so our second technology is the kinetic impactor, and in the same way, we also plot the delta V, in this case not as a function of the potential nuclear energy, but the total mass of that kinetic impactor. This total mass includes the maximum payload, the dry mass of the final booster, and also the dry mass of the payload capsule. So we see for the same asteroid diameter range, here instead of meters and centimeters per second, we can expect something like centimeters to millimeters per second, so quite a lot less than what we can expect from the nuclear impactor. By the way, this is for relative velocity of the kinetic impactor with respect to the asteroid of a modest 5 kilometers per second. If we increase this relative velocity to 20 kilometers per second, we see a slight improvement. You see there's more light colors for this asteroid diameter range. But just to give you guys a real-world feeling again, what we can achieve, I highlighted these two data points. So these two data points are for a Delta IV Heavy loaded with its maximum payload and impacting on a 300-meter diameter asteroid. And like I said, for these respective relative velocities, we can expect like millimeters per second or sometimes even centimeters per second. Then the final result is for the gravity tractor. Here we considered a maximum gravity tractor mass of 20 tons, and for each of these masses, the maximum thrusting power that gravity tractor could have is about 1 Newton. And for those of you interested, 1 Newton of thrust power is equivalent to about 10 of the ion thrusters on one of the current Deep Space One missions. And at first glance, the values here for delta V seem promising. It's sort of in the same range as the kinetic impactor, but there are two important things I have to highlight here. First of all, this is for a smaller asteroid diameter range. And secondly, because this is a cumulative technique, so not an instantaneous delta V you apply, this delta V plotted here is not instantaneous delta V, but a delta V that you can achieve per year. And if you take that into account, then these delta Vs are considerably less than the previous two examples. However, the gravity tractor has other advantages that still could make it an attractive option. Okay, so let me go back. So the plots that I showed here give us the delta V for each technology, but it doesn't really give us a full understanding of the capability to actually deflect an asteroid for each technology. And to do that, we can go back to the graph that Adam showed. Just to remind you, this shows the predicted success rate when you apply this delta V at a specific lead time. And what we can now do is we could try and fit one of the contour lines associated to a specific success rate. And this allows us, if we're given any lead time, I can give you the delta V required to achieve the success rate. Now with this lead time is paired an asteroid with a certain size. And if I take this asteroid size and I plug that into my technology calculations, I can calculate the maximum delta V that each one of these technologies can supply me with. And if this delta V is greater or equal to this required delta V, then I mark this technology as capable. And that's for the specific example of lead time and asteroid size. So I can do this now for all possible combinations of these two. And once I've done that, I can produce plots like these. And what's plotted here is the predicted success of each technology as a function of lead time and asteroid size. And this, as Adam said earlier, what's important here is that red means bad, so the technology is not capable, and blue is good. And as expected, for the most powerful deflection technology, For the most powerful diffracting technology, the nuclear impactor, we have mostly blue. There's only the small little slither here that we should be worried about. So any asteroid bigger than 600 meters and with a lead time less than 1 year, then we're going to have a problem. For the kinetic impactor, there's quite a lot of red, but there is some blue, so there is some impact scenarios that the kinetic impactor will work. For the gravity tractor, it's a lot worse, especially for very low lead times, but there is this promising linear behavior here, meaning that even though the delta V's you can supply here are low, if you have long enough lead time, even the gravity tractor would be able to still deflect even pretty large asteroids. So these three graphs can really be useful for deciding which technology to use. But one thing that is seriously lacking here is the underutilization of the orbital parameters. So this analysis is really nice, but I've sort of completely ignored the orbital parameters. And this could be a rich source of information. And Almarie will now show us how machine learning can be used to fully explore these orbital parameters.
Thanks, Nick. So the next component of our framework that we're presenting here today is using machine learning to find these mappings. So we train a machine learning algorithm to help us predict whether any new potentially hazardous objects could be deflected. Broadly speaking, machine learning are algorithms that map inputs to outputs. So in this case, if you have inputs, you find the mapping that gives you the outputs that you know of in the training set. And then when given a new object that wasn't part of your training set, you can predict where in the space it will lie, and then which output should be labeled, at which output it should be labeled as. In our case, the inputs were, after all of the data that we generated, the inputs are the orbital parameters. So these are the parameters that Nick just alluded to that wasn't included in his analysis. And then it's about the object. So the beta parameter is related to the composition, the structure and the composition of the asteroid. D is the diameter of the object, and then the lead time, as Erica showed, how much warning time do we have that this is going to that this object is going to impact us. And then the machine learning algorithm finds the mapping and telling us whether, with all of those parameters, this object is able to be successfully deflected or not. And then it will also tell us if we have a successful deflection, which technology could be leveraged to actually impart the necessary delta V. So the algorithm that we chose for doing this mapping is a decision tree. And the reason we chose it, I'll tell you now what a decision tree is, but the reason we chose that is it's very intuitive because you basically make decisions at each step of the tree to decide which way to go. So it's a very intuitive method, it's very quick, and you have to do very little data pre-processing if you want to apply it. So a decision tree is an algorithm that tells you which questions to ask about your data, such that it will provide the most information for selecting the right technology. So in a more practical way, what that means is if you choose one of your parameters, in this case delta V, then you find a split in that multidimensional parameter space that maximizes the information propagation. So if you've split your multidimensional space into an optimal split, then you go to the next, you branch off, and then you, at the next nodes, you choose again one of the randomly choose one of the features, and then it splits the multidimensional space even more that you gain information. And then ultimately it terminates when it results in a decision or when you actually tell it to stop, where you prune the tree. So what we did is we had about 42 million samples where we combined all of the orbital parameters plus the masses or diameters and then different beta parameters. And we trained on 80% of that data and tested on 20%. And we did a cross-validation of 10 times. And our accuracy rate is 97%. And that just tells you that the features that we have, although it's only 6 features, it's quite descriptive, and it's to say whether a deflection is possible or not and which technology to leverage. Yeah, so one last thing. we said in the beginning of the talk that if we plot all of the data that we have and all of the simulations that we run, that we would be able to draw some conclusions of which technology to invest in, or which technology is most likely to help us out in a tough situation. And at this point, I will give it back to Erica to reveal to you what our final conclusions and findings are.
Okay, so once we finish training the machine learning algorithm, now we're able to ask it that question that I was talking about at the beginning. Given the possible impactors that might hit us and the population of those impactors, which technologies do we want to use? From our preliminary data set that Nick and Adam just talked about generating, the solution that we get out of the machine learning algorithm looks like this. So it's telling us that for the objects that can be successfully deflected, the technology that works best, and in most cases, is the nuclear explosive, followed by the kinetic impactor, followed by the gravity tractor. And this is kind of what you would expect due to the fact that nuclear weapons carry the most amount of energy and gravity tractor works the slowest. So now that we have this proof of concept, the exciting thing is we can take this algorithm and go to the next step where we start feeding it more and more accurate impactor populations so we can improve the accuracy of this plot. Another thing we can do, as I mentioned at the beginning, that this model can do is we can look at how the different parameters affect this final answer. So far, based on the basic data that we're giving it right now, we can tell that about 80% of the decision is based on the lead time that you have, which is, again, is not a surprise. So our next steps are all about improving this model so we can get the most realistic result here that we can. One of the first improvements we'd like to make is about that lead time. The reason it depends so much on lead time right now is because we're just giving it random lead times. And that's a very important characteristic for which deflection technology you can use. So the next step is to make those lead times more realistic. For example, larger objects are going to be detected sooner than smaller objects, so you'll have more lead time to act. And that will probably affect this plot. There we go, this plot. So for example, once we add that detection effect, then it's possible that the gravity tractor will become less successful in the overall population because it works best on small objects with long lead times, whereas we tend to detect larger objects first. Another thing that we'll be able to add in very soon is the travel time. So how long does it take your technology to actually get to the impactor? As Adam mentioned, one of our assumptions is that you can get to any part of the impactor orbit, but that's actually a challenge depending on how much energy it takes to get there might affect how successful you are at reaching it in time. Another thing we'd like to add is the comet population. I mentioned at the beginning of the talk that comets are also a threat. They're a different kind of threat than asteroids. They're a much less known population, much less studied. The objects tend to be bigger and they tend to be coming in much faster with higher energy. And so including this population might really change that distribution of what technologies we need to consider. We'd also like to add more object parameters beyond just the size and the basic beta parameter we use to describe the internal structure. One of the things in particular we'd like to add is the spin period. How fast is the object rotating? That can really affect how well your technology works, especially for some of the other technologies we haven't studied yet. Speaking of which, there are other technologies we haven't studied yet and would like to be able to add. We've started with just the 3 most plausible ones. They're some of the best studied in the literature, and they're more likely to be developed sooner. But other technologies we'd like to look at include thrusters, the mass driver, which is illustrated here, and laser or solar ablation techniques. And again, some of these will really depend on understanding the spin period of the object well. And so these are our next steps as we continue to work past this program. We're going to be continuing to evolve and improve the model and the machine learning algorithm that we've built so we can come up with some good physics-based machine learning explanation and advice to give to policymakers to tell them which technologies we're going to need to focus on next. Thank you very much.